Good day, my lovely learners. On our series of Laplace transformed, we established the fact that we want to solve Laplace transform for differential equations. And before we can do that, we must look at Laplace transforms of derivatives. And so in this video, I'm going to take you through the Laplace transformation of derivatives. And you know what derivatives are. But before that, let me have this equation. We have established the fact that the Laplace transform of a given function is given as the integral 0 to infinity, the kernel function as exponential, and the function the t. Based on equation 1, we would have some identities known. So let's start with the first derivative. Assuming my f of t is, I'm looking for the first derivative, so the Laplace transform of the first derivative. What is it? I'm going to use equation 1. So this is the same as 0 to infinity, the kernel, times, now my f of t is the first derivative. How do I solve this? Is that simple integration? Yes. Because I have the function t here and then t here, I have to use integration by part. And I hope you know how to do that. So I will set some u. If I'm using this acronym, it means I can take exponential function first. So u can be my exponential function. It means my du is negative s, that's dt. And I set my dv to be the derivative. It means my v is integral of the derivative, which is simply going to reduce the order to f of t. Differentiation increases the order, integration reduces the order. So by substitution, I'm going to have it as, it means I'm integrating some u dv, which is the limits of this minus integral v du. By substitution, I have my u as that, my v as this, so 0 to infinity, my v as f of t, and du. So this is what I have, negative s f of t dt. By the method of substitution, I have infinity of infinity minus e of 0 f of 0 as one component. If I take those negatives out, I'm going to get positive s integral of the exponential function. You know this goes to 0, but this goes to 1. It means I have negative of the function at 0 plus the s of whatever I have here. That is Laplace transform of the first derivative. So the question is, can you redo a substitution? You realize that from equation 1, it is what we are seeing here. Let me change the pen. This entire expression here is having the Laplace transform of f of t. That is from equation 1. This is it. So I just do a substitution into that. Let me rewrite this as Laplace transform of the first derivative is equal to s, the Laplace transform of my t, minus my function at 0. So this is equation 2. That's the first derivative. If I want the second derivative, Laplace transform of the second derivative of that, you realize that I have to differentiate equation 2, or I have to go back to equation 1 and differentiate it twice. It's the same thing. It means I'm looking at d dt of my first derivative. This is the same as Laplace transform of d dt of this, which will give me the second derivative. So what do we have? I go back to have it as Laplace transform of my s let me do this well. So this is the same as I'm taking the Laplace transforms of ddt of this of s Laplace of f of t minus f of 0. This is what I'm doing. I'm able to write my Laplace well. Okay. Now this is the same as my s. If I take the ddt, becomes Laplace of f prime of t minus, this is not going to be 0, it's going to be the first derivative. Why? This f of 0 is not equal to 0. It is a function at 0. It will be equated to something we must look for. So it is not a constant. It's not equal to 0. It is a function, so it will have to take a derivative at whatever that functional value is. So that's what I have. Now we've already looked for this guy, which is equation 2. So by substitution, I have it as that Laplace of f of t minus f at 0. Then I have my last term here coming here as f prime at 0. I can expand this and have it as square Laplace of f of t minus s f at 0 minus f prime at 0. This is the second derivative. So I'll label that as equation 3. Now if I want to find the third derivative, so Laplace of the third derivative, it is the same as ddt of what? The second derivative. Differentiation increases the derivative. So I have ddt of s square Laplace of f of t minus s of f at 0, and then the last term. X is a constant, so I have s squared dt becomes Laplace of the first derivative, ddt applies to this, minus s, the first derivative of 0. If I explain why it is not 0, there's a first derivative. Then what do you think happens to the second part? It becomes the second derivative because it's already in the first derivative, and so an additional derivative makes it twice. Now I can do a substitution here because I know this function here. It is from equation 1. I've already solved for that. From equation 1, it is s. So let me change the pen for the substitution. From equation 1, let me just get that off head. It is SL left t minus that. So there's the L Laplace of f of t minus f at 0. This is at, like, continue the rest, minus f prime at 0 minus the second derivative at 0. Expanding this, I have cube Laplace of f of t minus s square f at 0 minus s f prime at 0, and then the last term holds. This is the third derivative, equation 4. And so with this, I can find the fourth derivative, I can find the fifth derivative IV, I can find the v, f of v, I can even find the sixth derivative, and so on up to the nth derivative, the Laplace transform of all these. Now someone said, do I have to wait? So if I want to find f of 6, do I have to start from 1, 2, 3 to get the fifth one before I can differentiate the fifth one to get a sixth? No. And so you can see a recurrence pattern here. Let me help you out to visualize that. Let me have it as a table. If I have f of t's, I have Laplace transform of f of t, which I can write it as big F of s into the frequency domain. We realized that when it was the first derivative, we had s Laplace of f of t minus f at 0. When it was the second derivative, we had s square minus s f at 0 minus f prime at 0. I hope I'm correct with that substitution. Yeah, I'm correct. Let me just confirm. Yeah, sorry for the scrolling up and down. When it was a third derivative, we had cube Laplace transform of f of t minus s square f at 0 minus s f prime at 0 minus f prime at 0. Do you think you can write the fourth one? So what do you think the fourth IV of t would be? If I follow the pattern, I'll have 4 Laplace of f of t minus 3 cos c 1 0 2 1 0 3 to 2 to some 1 to some 0. So it means there's some reduction of the indexes on the frequency. So I have f cubed at this minus, it should go to s squared, the first derivative, minus now s to the second derivative, and I can have the third derivative when s is 0. So you realize that if I have f of an nth derivative, I have it as the first n, and then you know that everywhere I have L of f of t, it is equal to big F of s. So I want to do the replacement. So I have f of s minus, you realize that with n index is reducing. When it reduces, it's no more the big F, it is just the f at 0. It would reduce again to n minus 2, and then the first derivative at 0. We reduce again to n minus 3, and then we're going to take the second derivative at 0 through to, so let me do it, my dot minus. When I take it to the last term, s at 0, I'm going, or s at 1 should reduce the first one. It's going to take f of n minus 1 at 0 through to the last term, which is f n minus 1 at 0. Here it means that s is to the power 0. You know what s to the power 0 means? It is 1. This is the pattern. So let me help you with that. You realize that s will move from some n to some 0, and then the powers of f is moving from n minus 1 from the first derivative through to n minus 1. So let me put a bracket here. They know these are indexes or powers or exponents. Here are derivatives. So 1, you know, it is the same as prime. If I have 2, you know, it's the same as prime. So if I have n minus 1, the same as n minus 1 term derivative. So that's why I have them in the bracket. Sorry, start from 0. 0 means that there's no derivative to n minus 1. So I can have a recurrence formula such that Laplace transform of the nth derivative is equal to the first term minus, if I want to take off this nth component, which is here, I have it as summation I running from 1 to the nth term s n minus I f I minus 1 of 0. This recurrence formula should just help you. So I'll label that equation star star, and you can verify them. Let's do the verification. You realize that if I want to find f1, that means n is equal to what? 1. I'm going to get s to the power 1, f of s minus summation I will run from 1 to 1. Sn minus I fi minus 1 of 0. This is the same as, since I is just running from 1 to 1, it means I'm taking when n is 1. I have s 1 minus 1 f 1 minus 1 of 0. This is 0, s to the power 0, f 0 of 0. Now this is an index, so s to the power 0 is 1, but this is not an index. It means there's no derivative of the function, and we've established that. When n is equal to 2, I'm taking just the last one. From the formula, I have Laplace of the second derivative. It means I'm taking it from s to the power 2 f of s minus summation I running from 1 to 2, s taking n to 1, f taking n minus 1 of 0, the functional value there. When n is 2, I have square minus, so the first, when I equal to 1, at I equal to 1, I have it as 0, f at 0, 0, plus at I equal to 2, I have it as s 1, and 2 minus 1 is 1, and then f here, 2 minus 1 is still 1 of 0. This is equal to this minus, this is index, so this goes to 0, so I have it as the first derivative. Since this goes to 0, this means there's no derivative. F at 0 means no derivative, so I have it as just f at 0. The negative is running through, so minus 1 means 1, and then first derivative at 0. So f to the power 1 means the first derivative. And I've confirmed equation 2, or the second derivative. And so this is how we get the recurrence formula. You don't have to just memorize equation star, but know how equation star was derived. Assuming you forget, you can go through this, establishing your first derivative, and then use that to find the others. I hope this video would be helpful in taking you through the last thing as solving differential equation with Laplace transform. If you don't know the Laplace transformations of the derivatives, you can't solve or evaluate differential equations with Laplace transform. So that'll be my next video.